Hello, good morning all. I am Dr. Abdul Pasha, working as Assistant Professor in Institute of Aeronautical Engineering, Dundigal, Hyderabad, in the Department of Electrical and Electronics Engineering. So here I am in the course of Power System Operation and Control. So it is about the discussion regarding shunt series compensation strategies. So this is mostly referred in the power system network, as the networks are suffered from the power factor lagging cases. So here reactive voltage ampere compensation involves. That means it is the management of reactive power for the improvement of whole electric power system performance. So here it will be adequate in nature that reactive power control solves the power quality problems like flat voltage profile maintenance at all the power transmission levels, and also it improves the power factor, transmission efficiency and the system stabilities. So series and shunt wire compensation techniques are mostly modified as the natural electrical characteristics of the whole power system network. So series compensation ready to modifies the reactance parameter, which is of about transmission or distribution network. So while shunt compensation ready to make the changeover for equivalent load impedance characteristics. So here in both the cases, the line reactive power can be effectively utilized, thereby it should be improving the performance of the overall electric power system. So here it will represent the reactive power and static wire compensation technologies. So in this study, we will introduce the results which are obtained both in the series and shunt reactive voltage compensation. So these techniques are usually taken as one of the case studies which will be make sure about how the compensation strategies they may go to vary. So in general, modern civilization is mostly depends upon the electrical networks that should be implemented in agricultural, commercial, domestic, industrial and social purposes. So this is exclusively generated, transmitted and distributed in the form of alternating current, that is called by AC, of three basic elements of electrical engineering. Like resistor will ready to consume ohmic energy, whereas inductor and capacitor stores electrical energy in the magnetic field aspect and electric field respectively. So here the total amount of power being utilized or dissipated in a circuit is called as true or real power. These are the basic fundamental. So reactive loads such as inductors and capacitors, they are ready to dissipate zero power. If the drop voltage and draw current giving the dissipative impression that they actually do the dissipation of the power respectively. So this may be treated as one of the phantom power, which is called as reactive power. So reactor or capacitor stores the reactive power generated by the AC power source. This will be during a quarter of a cycle and it will returns to the same power to the source in the next quarter cycle. So in other words, we will treat the reactive power oscillations in between the source and the reactor or in the capacitor. This should be treated at any frequency equal to the twice the rated value. So more precisely, power dissipated by a load is referred to as true power, whereas power merely absorbed and returned in the load, this is due to the reactive power properties, they are referred to as reactive power. So however, in nature most of the loads are inductive in nature, so they are absorbing reactive power and resulting in low lagging power factors. So here are some of the effects of reactive power flow in the line network. That is, the first thing is poor transmission efficiency. So losses in all the power system elements from the power station generator to the utilization devices, they are ready to increases due to the reactive power drawn by the loads. So thereby they may ready to reducing the transmission efficiency. So here the poor voltage regulation is due to the reactive power flow in the lines. So voltage drop in the lines may got increases, due to which low voltage is ready to exist at the bus nearer to the load and makes the voltage regulation to be very less or poor. So here, coming to the low power factor case, operating power factor reduces due to reactive power flow. So that may happens in the transmission network. So here there is a need of large sized conductors. So that low power factor due to reactive power flow in the line conductors, that will necessitates the large sized conductors. They are ready to transmit the same power when compared to the conductor. They are operating at high power factor case. So here is increases in kVA rating of the system equipment. So reactive power in the lines are directly affecting the kVA rating of the system equipment. So they will carry the reactive power, and hence these affect sizes and costs of the equipments directly. So reduction in handling the capacity of all the system elements are taken place. So that reactive component of the current ready to prevent the full utilization of the installed capacity of all the system elements, and they hence reduces their power transfer capability. So here a power system is expected to operate under both normal and abnormal conditions. Under these conditions, they decide that voltage must be controlled for system reliability, and the transmission loss should be reduced, and the power factor should also be improved. So here the effect of line reactive power flow on the transmission efficiency is mostly considered as one of the suitable parameters. So, and also it is associated with voltage regulation and power factor with and without wear compensation. That techniques are analyzed and presented here. So effect of reactive power flow on the line voltage drop. So what happens with this case means, voltage variation is due to the imbalance in the generation and consumption of reactive power in the whole system. So if the generated reactive power is more and more than the consumed one, then voltage levels goes to up and vice versa. So however, if the two areas are equal, then the voltage profile becomes flat, and it happens only when the load is equal to the natural load case. So unfortunately, reactive power in a systems are keep varying, and if the reactive power generation is simultaneously controlled in a more or less, then flat voltage profile could be maintained easily. So there should be the one of the lamp characteristics in case of lightning load conditions. So they are very sensitive to the voltage changes, and that voltage variations may causes erratic operations in case of power loads. So for example, if the supply voltage exceeds the rated value, motor magnetic circuit may goes to be saturated, and consequently it draws the large magnetizing current in the system. So on the another hand case, if the voltage is very low, then starting torque becomes low, so it will be very large variations in the voltage, which causes excessive heating of the distribution transformer. So thereby it will reduces the transformer rating. So voltage profile must be within plus 5 to 6% of the rated value for better and efficient operation of the electrical equipment. So as most of the loads are operating at low lagging power factors, they require significant amount of lagging reactive powers during the peak load conditions. So however, if the significant amount of lagging reactive power is there, that should be supplied by the generators from the sending end, then all equipments are starting from the sending end. It may be overloaded, thereby causing low receiving end voltage case. So during off-peak load conditions, line generates net reactive voltamps, which must be absorbed to obtain voltage stability. So shunt compensation involves use of shunt capacitors during peak load conditions, that is to generate lagging reactive voltamps at the receiving end, and shunt reactors during off-peak load conditions. So this is ready to absorb the line generated reactive voltamps to avoid the voltage instability case. So when there is an instability in the voltage, that may causes the load impact. That means load may got disturbed, due to which malfunctioning of the load equipment may causes. Here I am showing one of the figure that will represent the equivalent circuit of an AC generator supplying power to a practical inductive load, and it is also represented with one of the phasor diagram. So the diagram shows here with the source voltage E and one of the components R plus J XL and real and reactive power coefficients with P plus JQ manner. Here the voltage appears will be V at that instant. Then the total amount of current flowing through this becomes as I. So due to which the one of the reference phasor selected here is V. So with respect to this reference phasor, the voltages which are supposed to be phase with the delta case, and these are lagging with the angle phi, that is displaced by an angle phi lagging with current I. So one of the drops with R and X as IX and IR. IX and IR cases are represented, where that IX drop is represented with one of the coefficient called delta V, and IR coefficient is with one of the delta V. This delta is different with this delta cases. So this may be one of the equivalent circuits of alternator. They are supposed to supplying electrical energy to a practical inductive load, and this is the one of the suitable phasor diagram case. Here are some of the important relations representing from the phasor diagram, that one of the voltage as square term, they are supposed to be aided with the source voltage V plus change in voltage delta V whole square plus delta V whole square coefficient. So when you take the A plus B whole square concept, then this V becomes V square plus delta V means it is associated with IR cos phi plus IX sin phi. So this combination is substituted in terms of delta V case, and also this delta V will be represented with IX cos phi minus IR sin phi case. So when you substitute these coefficient and representing to the terms V plus RP by V as one of the common coefficient, and XQ by V is another coefficient as whole square term, then XP by V minus RQ by V as one of the whole square term is taken. So therefore delta V becomes RP plus XQ by V is considered, and delta V becomes XP minus RQ by V. For delta V, which subtends to V plus delta V coefficient, as E minus V is treated as delta V, this is represented with RP plus XQ by V coefficient. So XQ by V is very much less than with R less than X. That means what's happening here means the drop in voltage depends upon the reactive term coefficient, that is Q. So if reactive power flows over the transmission line, then there will be a voltage drop expected in this system. So what are the effects of reactive power flow on transmission efficiency and power factor? So here it is desirable for both economical and technically to operate the electrical power systems at nearer to the unity power factor case. That means usually power factor correction is ready to generate reactive power as close as to the load which it requires generating at a distance and transmit it to the load. So because of this results, doesn't need to large sized conductors, but also it will be increases losses, thereby reducing the transmission efficiency. That means one of the efficiency factor may goes to reduces. Likewise, efficiency of the transmission system may ready to decreases. So here one of the compensation strategies are developed with the artificial injection of the reactive power at various loads may rely with the transmission network from the reactive power flow condition. So it also improves both the transmission efficiency and operating power factor, whereas artificial injection of negative reactants and the lines may rely in the lines from the excessive voltage drop, and it also improves the voltage regulation of the system. So these methods are available for the injection of both static compensation and synchronous compensation methods. So static compensation involves with the capacitors and the reactors injection, whereas synchronous compensation involves with the synchronous phase modifiers conditions. So here principles of both shunt and series compensation techniques are represented. When you go with the shunt compensation method, what happens means at the buses where reactive power demand is going to increases, QP is going to increases, bus voltage can be controlled by connecting capacitor banks, that is in parallel to the lagging loads. So because of this, capacitor bank supply part of the full reactive power of the load, thus it will reduces the magnitude of the source current that will be necessary to supply the load current. So consequently, voltage drop between sending end and the load gets reduced, power factor will be improved, and increase in active power output will be available from the source, that is in megawatts case. So based on the load demand, capacitor banks may be permanently connected to the system, or they can be varied by switching on off by the parallel connected capacitor. So they may either manually or automatically controlled by this condition. So here one of the diagram shows how the single line diagram of a transmission line and its phasor before the addition of the shunt capacitors, that will represented here. This diagram may be treated as one of the uncompensated line. So uncompensated line contains equivalent R in series with the inductive reactance parameter excited by one of the source Vs. So when it is connected in series with the load, then drop across it will be considered as one of the VR case. Here is the phasor diagram representation. Here the reference phasor becomes VR. With respect to the reference phasor, one of the two angles delta comma phi are supposed to be displaced. So delta is displaced with one of the source voltage and phi is displaced with lagging power factor with current I. So this drop summations may be treated as one of the coefficients of IZ, IXL and IR case. These are one of the drop coefficients that may be treated in the whole phasor diagram. So here it is about single line diagram and the phasor representation when we are supposed to aiding the shunt capacitors. So what happens when you add a shunt capacitor? Here this is the addition of shunt capacitor into the system. This network is equivalent series R and XL combination. They are supposed to be connected by one of the capacitive reactance in parallel with the load. So here the drop expected becomes VR. Then the phasor will be taken as one of the reference VR displaced by angles phi dash and delta dash. So the lagging currents, they should be according to the phi dash as II dash with the one of the coefficient IC. They are displaced by angles delta dash phi dash, means the drop expectancies in terms of I dash Z, I dash XL and I dash R. These are one of the drop expectancies when you are aiding the capacitor. Then because of the compensation of this capacitors, then line will be energized more with respect to the load conditions. So here use of shunt capacitor banks are suffering from one of the following drawbacks, that are shunt capacitors, they do not affect the current or power factor beyond the point of application. That means reactive power supplied by the shunt capacitor banks are directly proportional to the respective bus voltage. So when the reactive power required is less on the light load conditions, capacitor banks output will be high. So the disadvantage can be eliminated by connecting number of capacitors in parallel, and the capacitance can be varied by switching on or off depending upon the load requirement case. So here series compensation is introduced. When the line has high value of reactance to the resistance ratio, that means reactance X by R is high. So inductive reactance of the transmission line can be decreased by introducing series capacitors, which may result in low voltage drop. So if a capacitance C with reactance is connected XC, that means in series with the line, then reactance will be reduced to XL, XC parameters. So due to which voltage drop is reduced, furthermore reactive power can be taken by the line also to be reduced. So this is the diagram showing single line diagram of a series compensated transmission line with its phasor diagram. Here we are making series compensation. Earlier we taken a parallel combination. So series compensation means with R and XL coefficients we are adding series XC. That should be excited with source voltage Vs and one of the load here, across which VR is considered. So reference phasor is VR. With respect to that, one of the angles are displaced by delta and phi. So with this, the drop of lagging currents are with IXC drop and inductive drop will be IXL coefficient. So this net drop will be one of the XL minus XC coefficient with IZ dash is considered as IR drop. This may be treated as one of the single line diagram of series compensated transmission line with phasor diagram. So likewise, with the use of series capacitors to reduce the voltage drop in the lines with low power factors, and it will improve the voltage profile at the receiving end, particularly with low power factor load conditions. So for variable load conditions, voltage can be controlled suitably in suitable series capacitors in the line. So under short circuit conditions, produced high voltage may be damaged by the capacitors. So series capacitor has to be protected using one of the spark gap arrangements with high speed contactors. So this use of series compensation will introduce to some of the problems like subsynchronous resonance, XS. Subsynchronous resonance is created, and also it is associated with ferro resonance with high recovery voltage are going to be generated in this system. So here one of the case study is made. In this case study, it should be carried out with the improvement of voltage regulation as transmission efficiency and power factor objectives are maintained under load voltage constants. So at a three-phase induction motor given from the feeder, then it should be representing that one of the feeder that is connected with the three-phase conductor management, they are connecting to the one of the induction motor case. What happens to with this means the line is energizing with the one of the three-phase conductor arrangement with one of the induction motor case. So here it is the system data considered for induction motor with type of the machine is three-phase and the frequency considered about 60 Hz. The type of the connection generated for induction motor will be star connection, and one of the rating of the machine in horsepower will be 500 HP and voltage rating at 4.160 volts. Full load efficiency becomes 88%. So power factor will be lagging in nature about 0.75 and the resistance is about 0.16 per phase. And inductance is about 1.029 millihenries per phase case. So this is about base case or uncompensation results. When the system is not compensated, then these are the absolute magnitudes generated in terms of load current. High load as 78.4 amps. Line current becomes 78.4 amps. Phase voltage drop becomes 32 volts. And the line voltage drop becomes 57 volts. Sending end voltage as 4.217 volts. And total reactive power loss in terms of 2.95 kilowatts. And the reactive power loss as a total in case as 7.161. Sending end reactive power is about 426. And this is about to power factor in terms of cos phi as 0.746. And load power factor will be operated at 0.75. So series capacitors are usually selected such that line inductive reactance is more than the capacitive reactance. So assuming that each phase capacitive reactance are equivalent to 0.25 ohms. So this is the case of series capacitive compensation. When the compensation is done, how these factors will influence parameters. Load current is 78 amps, line current is also 78, phase voltage drop 16 volts, line voltage drop is 28 volts, and the sending end voltage 4186 volts, and total active power loss 2.95 kilowatts, reactive power loss 2.54, and this sending end active power becomes 426, and because of this it will generate sending in reactive power 376.3 and system power factor 0.75267, load power factor becomes 0.7. So assuming the power factor to be improved here to 0.9, it shows the magnitudes of different parameters with the shunt compensation techniques like capacitive current. Shunt capacitive compensation results gives capacitive currents IC 23 amps and line current 65 amps, phase voltage 27 and line voltage drop 47, sending in line voltage 4207 and total active power loss 2 kilowatts, reactive power loss 4.9 kVAr, sending in active power is 425 and reactive power is 210 kVAr. So capacitive reactive power requirement becomes 168 kVAr. Line reactance also 205. System power factor is 0.89. That means almost it reaching to 0.9 case. Load power factor is maintaining same 0.7. So comparison among the effect of uncompensated line, series compensated line and shunt compensated line on line voltage flows power factor are taken place for each system. So this is the comparison results when it is taken place with the parameter source voltage from line to line, then base current arrangement and series capacitor arrangement, shunt capacitor arrangements are considered. Vs is about 4217.05 volts, series capacitor arrangement 4188 volts, shunt capacitor is 4207 and the total load power becomes 2.95 kilowatts and capacitive arrangement also same, but coming to shunt capacitive arrangement it will be changes as 2.052. So total reactive Coulomb coefficient becomes 7.161 kVAr, this becomes 2.547 kVAr and this is 4.97 kVAr. So cos phi has 0.746 and this is about 0.7526, this is about 0.8966. So cos phi L becomes 0.75, here 0.75, here also 75. So all the same combinations may be existing for comparison of all the results which are existing in the whole system for various voltages, powers like real and reactive term coefficients in terms of angles, systems and load considerations are going to be treated very mostly. So coming to the conclusion here, to maintain the constant load voltage, we should treat voltage, sending in voltage to be maintained with low with the series capacitive arrangement than with the shunt capacitive arrangement. So shunt capacitive arrangement ready to reduce the total active power loss while series capacitive arrangement does not affect mostly, and series capacitive arrangement reduces the total reactive power loss while series capacitive arrangement does not affect mostly. So series capacitive arrangement are ready to reduce the total reactive power loss by a large margin as compared to the shunt capacitive arrangement. So shunt capacitive arrangements are ready to improve the system power factors thereby a large margin as compared to series capacitive arrangement cases. So load power factor also remains same here, that means constant with and without any compensation strategy or method. So these are the conclusions which are derived for making suitable shunt and series compensation strategies. So these are one of the references whichever I have considered from IEEE transactions, Bhattacharya, Fernando's, and that is from one of the source objectives from determination of location and the amount of series compensation strategies. These are ready to increase the power system capabilities and efficiencies. Whatever the conclusions suggested in terms of shunt and series compensation strategies. So they will make sure about the system compatible levels with increase in order of the whole system considerations. So with this we can make the entire line to be energized suitably and which will give the suitable results to operate perfectly with all the magnitudes generated in the system, and they can sure about that which will be operated effectively. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.